The morning of August 21st, 1944, a damp breeze rolled inland from the waters of the inland sea, brushing across the runways of Tachikawa Air Arsenal, just west of Tokyo. In a hangar smelling of aviation fuel and machine oil, a team of engineers in oil-stained coveralls circled a battered mass of aluminum and wiring laid out on trestle tables. The object looked like a relic from another civilization, complex, elegant, impossibly foreign. Lieutenant Commander Tadao Ueno, of the Imperial Japanese Navy's Aeronautical Technical Institute, adjusted his glasses and bent closer to the strange mechanism. The brass data plate still bore English lettering, scratched but legible. Automatic Flight Control Equipment, Sperry Gyroscope Company, Brooklyn, New York. What Ueno and his team were examining that day was the heart of a machine that had haunted Japan's skies for months, a fragment of the American Boeing B-29 Superfortress. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Only weeks earlier, the wreckage had been brought from a rice field near Yawata after a desperate night of anti-aircraft fire. Among the twisted sections of fuselage, technicians had discovered a sealed metal box with thick bundles of color-coded wires leading to gyroscopic instruments and electric servo motors. To the ground crew who first pried it open, it looked like a tangle of small turbines. To Ueno's scientists, it was something far more consequential, the first intact example of an American autopilot captured on Japanese soil. No one in that hangar realized that they were staring at the technological core of a new kind of warfare, a machine that quietly erased the line between pilot and computer. The Japanese engineers had been taught to believe that their aircraft, lighter, simpler, and guided by human intuition, represented the pinnacle of aeronautical art. Yet the tangle of American wires before them would soon force a reckoning they could not have imagined. For the previous 6 months, Japan's mainland cities had lived under the distant thunder of B-29 raids. From bases as far away as Chengdu and later the Marianas, the Superfortress struck with an impunity that no Zero or Ki-84 could reliably challenge. High above 30,000 feet, unseen in the night, it was guided not merely by pilots, but by an intricate network of servos, gyros, and vacuum tubes systems that allowed it to fly hundreds of miles on preset headings, maintaining altitude and course with mechanical precision, even in turbulent air. To most Japanese airmen, this idea bordered on myth. The Imperial Navy's best autopilot, the Type 1 automatic flight device fitted to late-model bombers, could maintain level flight only for a few minutes before drifting. No domestic instrument maker, not Tokyo Keiki, not Mitsubishi Electric, had produced a gyroscope stable enough for long-range navigation. Japanese doctrine placed faith in the pilot's senses, not in machines. The culture of the cockpit was built on discipline, intuition, and endurance, not automation. But the B-29 was something else entirely. It was a system, a flying machine that fused industrial mass production, electronics, and aerodynamics into a single philosophy of total efficiency. When Japanese observers recovered the remnants of one near Yawata, they were astonished by its materials alone. Magnesium alloy castings, seamless hydraulic lines, and electrical connectors more intricate than any domestic equivalent. Yet the true revelation lay in the device now sitting under laboratory lights at Tachikawa, the Sperry A-5 automatic pilot. The A-5 was no simple stabilizer. Developed in the late 1930s, it used 3 independent gyroscopes, a set of amplifying servos, and an electro-pneumatic interface, linked directly to the aircraft's control surfaces. It could hold a course through cloud or darkness, correct for wind drift, and coordinate with the Norden bomb site so that, at the moment of attack, the bombardier could take over guidance seamlessly. In American terminology, it was coupled flight control. In Japanese terms, it was sorcery. Ueno's team began disassembly on the afternoon of August 22nd. They worked in silence, broken only by the hiss of soldering irons and the rattle of small screw boxes. Each new component exposed layers of precision they had never encountered. Vacuum-sealed gyros suspended on jeweled bearings, amplifiers using miniature triode tubes, wiring looms wrapped in color-coded insulation of a synthetic polymer they could not identify. One engineer remarked that even the solder joints seemed uniform, machine-made, not hand-tinned. Their own gyro units, by contrast, required constant calibration and failed under sustained vibration. This American system had evidently run for hours inside an aircraft that had flown across oceans. At night, Ueno wrote in his notebook part technical record, part confession. "The circuits seem alive," he wrote. "They act upon the plane as if with thought. We build machines that obey." This one anticipates. That sentiment captured the broader irony of Japan's wartime technology. The empire that had prided itself on spiritual discipline and mechanical craftsmanship was now facing an enemy whose strength lay in systems engineering, the invisible architecture of automation, computation, and logistics. Through the summer of 1944, Japanese scientists struggled to reproduce what they found. The Naval Aeronautical Institute summoned engineers from the Tokyo Imperial University's Faculty of Engineering, as well as specialists from Hitachi and Nippon Gakki. They traced circuits, measured resistance, and attempted to map the logic of the autopilot's control loops. But the deeper they went, the more alien it appeared. One Hitachi technician later told interrogators after the war that the device represented a civilization organized for electricity. Japan, by contrast, was still organized for craftsmanship. Vacuum tubes were fragile, high-precision gyros, expensive, and production of stable amplifiers limited by shortages of copper and nickel. Even if they understood the A5 inches principle, the material base to duplicate it simply did not exist. Meanwhile, the raids intensified. From newly captured bases in the Marianas, entire wings of B-29 seconds began hammering the home islands. Each aircraft relied on its Sperry autopilot to hold formation through long night flights and turbulent weather. Japanese radar operators could trace their altitude and direction, but could not fathom how they maintained such perfect spacing and course, even when scattered by anti-aircraft bursts. By the autumn of 1944, fragments from 3 additional downed B-29 seconds had reached the research centers at Tachikawa and Yokosuka. Engineers compared them meticulously. Each contained the same gyros, the same vacuum amplifiers, and identical labeling evidence of industrial standardization on a scale beyond anything in Japan's war economy. The technicians could only marvel. Every component interchangeable, every circuit documented. Captain Yasuo Hino, a former flight test officer, recorded his impression after inspecting a complete A5 assembly. "It is not merely that it works," he said. "It is that it works the same way in every plane. That is the strength of their industry." The realization cut deep. For years, Japanese propaganda had portrayed Western machinery as cold and soulless, inferior to the intuitive skill of the Japanese pilot. But here, laid out under a magnifying lens, was proof that precision and repeatability, not intuition, had become the foundation of modern air power. The shock was intellectual as much as technical. Engineers, trained in a culture of secrecy and improvisation, found themselves confronting a design that assumed transparency and standardization. Every wire was labeled, every screw dimensioned. It was, in a sense, the embodiment of the American industrial mind trusting the system, not the artisan. Through late 1944, efforts continued to reconstruct a working model. The Naval Technical Arsenal fabricated mock-ups using domestic components, substituting locally made gyros and amplifiers. The prototype functioned for a few minutes before drifting wildly. The cause, investigators found, lay in the Japanese gyros themselves. Their bearings lacked the necessary precision. Their motor governors fluctuated with voltage. The technicians could only conclude that the entire electrical infrastructure, from copper wire purity to battery stability, would have to be rebuilt to match the American system's reliability. In a confidential memorandum dated November 10, 1944, Ueno wrote, "We have captured the form of the device, but not its spirit. Its operation depends upon a harmony of production far larger than the instrument itself. That memo would circulate quietly among senior staff before being filed away as unsuitable for immediate military exploitation. By the time the first snow fell on Tokyo in December, the engineers at Tachikawa had accepted what none dared say aloud. They were studying a machine at least a decade beyond their nation's reach. The new year of 1945 began under an empty, metallic sky. The once bright workshops of Tachikawa stood half-darkened to conserve electricity. Air raid sirens had become a routine punctuation of daily work, yet inside Hangar No. 4, where the recovered American Autopilot sat disassembled across a row of wooden benches, the engineers continued their examination with almost religious persistence. Every morning, before the first siren, Lieutenant Commander Ueno and his technicians gathered around the work tables. The room smelled of ozone and cold solder. The walls trembled occasionally from distant anti-aircraft fire. In one corner, a student assistant operated a small generator scavenged from a wrecked Ki-49 bomber, its irregular hum powering the oscilloscopes and galvanometers the team used to trace current through the captured device. By January, they had reconstructed nearly half of the Sperry A5's control circuitry. What astonished them was not any single invention, but the way each component functioned within a closed feedback system. The gyros sensed deviation, the amplifiers corrected it, the servos moved the control surfaces, all in fractions of a second faster than human perception. Japan's own automatic pilots were open-loop systems. They reacted slowly, never quite returning to equilibrium. The American design achieved stability through mathematics and manufacturing precision, a synthesis that could only arise from a nation where industry and science marched together. The deeper the engineers studied, the more they recognized how far their country had diverged from that path. In a memorandum dated January 15, 1945, Professor Kenjiro Takayanagi of Tokyo Imperial University observed, "This mechanism presupposes the existence of an electrical civilization. Every component, wire, valve, resistor, behaves predictably because it is made in millions." That statement, circulated quietly among research officers, struck like a revelation. The war had long been framed as a contest of will spirit versus materialism. Yet here lay evidence that material organization itself had become a kind of intellect. Outside the laboratory, the city of Tokyo was beginning to disintegrate under the weight of sustained air attacks. B-29 formations appeared by the hundreds, guided by the very instruments the engineers were now dissecting. The irony was merciless. Each night, the men at Tachikawa would watch from the airfield as the sky to the east glowed crimson over the capital. Then, in the morning, they returned to their benches to study the same technology that made that devastation possible. The Imperial Army's Technical Bureau requested an emergency report. Could Japan produce an equivalent device? Ueno's answer was measured, but fatalistic. He outlined the materials required: high-grade aluminum for gyro housings, precision bearings, miniature vacuum tubes, servo amplifiers with uniform gain, and concluded, the raw materials do not exist in sufficient purity, nor the factory conditions to produce them. The document reached Tokyo headquarters in late February. It was marked, for reference only. By March, the city itself had become a laboratory of destruction. The great firebomb raid of the 10th transformed eastern Tokyo into an ocean of flame. Many of the Tachikawa engineers lost their homes that night. When they returned to work, faces blackened from smoke, they found their generator seized for emergency communications. Still, they persisted, sketching circuit diagrams by candlelight. The last phase of their study came in April, when the Naval Institute secured a nearly intact Sperry gyroscope from a B-29 that crash-landed on the island of Kyushu. The crew had been captured. The aircraft was burned, but the instrument compartment survived. When Ueno's team opened the crate, they fell silent. The gyro's casing gleamed like jewelry. Every bearing ran smooth as water. The motor's balance was flawless. One of the younger engineers, a graduate from Osaka Technical College, whispered, "It spins as if in a vacuum." That evening, Ueno dictated his assessment. His tone was almost philosophical. "In our machines, error accumulates. In theirs, Error is the enemy. The difference is invisible but absolute. The Navy ordered that a small delegation present its findings to the Ministry of Munitions. The meeting took place in a reinforced basement under the Marunouchi building, one of the few structures in Tokyo still intact. Senior officers in white uniforms listened as Ueno described the autopilot's functions. When he finished, an admiral asked, "How many years would it take to equal this?" Ueno hesitated, then replied quietly, 10 years if we begin today, and if the war stops tomorrow." There was no reply. The men in the room knew the war would not stop tomorrow. In the weeks that followed, desperation replaced analysis. The engineers were ordered to design a simplified automatic control system suitable for use in special attack aircraft, the Toko missions the West would call kamikaze. The intent was to allow the plane to maintain a straight, level dive toward its target, even after the pilot released the controls. It was a cruel paradox. Technology intended to preserve life was now being copied to ensure death. The resulting device, the Type 99 Special Flight Controller, was crude, a single-axis stabilizer built from surplus gyro compasses. It worked poorly, but the symbolism was unmistakable. Japan's first attempt at autonomous flight control would guide aircraft not to return, but to vanish. By the summer of 1945, Tachikawa's laboratories stood half empty. Supplies had dwindled. Power was intermittent. The engineers packed their notes into wooden chests for safekeeping, unsure whether they would survive the air raids. On the night of August 15th, as the Emperor's broadcast crackled over the radio, Ueno sat beside one of those crates, listening in silence. Around him lay the disassembled parts of the captured autopilot, gyros, amplifiers, servos, mute witnesses to a vanished dream of mastery. He wrote one final entry in his notebook. "We studied the device to defeat it. Instead, it showed us the shape of another world. When the war ended, the airfields fell silent. The hangars at Tachikawa stood, like hollow shells under a sky that no longer trembled with the drone of bombers. Piles of burned aluminum and melted glass littered the runways, where engineers once sketched circuit diagrams by candlelight. In the final days of August 1945, Allied occupation forces arrived to inventory what remained of Japan's aeronautical research. Among the crates labelled automatic control devices for study, they found the disassembled components of the Sperry A5 autopilot, neatly arranged and catalogued in English and Japanese. The officers in charge of confiscating technology barely noticed. They were searching for rocket engines and jet prototypes, not obsolete fragments of electrical equipment. But for the few surviving Japanese engineers who had handled it, the loss felt personal. Lieutenant Commander Tadao Ueno was relieved of duty and returned to civilian life. He spent several months under quiet interrogation by American technical officers who questioned him about the state of Japan's electrical industry. His answers were brief, factual, and tinged with something that the interviewers later described as intellectual surrender. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. When asked what he had learned from the captured autopilot, he paused before replying. "We discovered that the machine was not only superior, it was coherent. Every piece existed for every other. That is the difference between construction and design." For Japan's post-war engineers, those words would become almost prophetic. In the autumn of 1946, the Ministry of Commerce and Industry, soon to become MITI, began recruiting former military scientists to rebuild the nation's electrical and precision instrument industries. The factories that once produced bomb fuses and gyro compasses were redirected to manufacture radios, cameras, and measuring instruments for civilian export. Many of the same men who had studied the Sperry device at Tachikawa found themselves teaching a new generation of engineers about systems integration, tolerance control, and mass production principles they had glimpsed too late during the war. Ueno accepted a post at the newly founded Japan Aviation Electric Company, a small enterprise tasked with producing flight instruments for the Allied occupation forces. Among its early projects was a simplified gyroscopic autopilot, modelled on the Sperry system, not a copy, but an interpretation built with domestic materials and post-war constraints. It could maintain steady flight for short periods, enough for training aircraft. Yet its greater importance lay in the methods it introduced: rigorous testing, statistical quality control, and documentation. From those seeds would grow the ethos of Japan's post-war industry: precision without mysticism, craftsmanship disciplined by data. Across the Pacific, American engineers also revisited their wartime inventions. The Sperry A-5 evolved into the A-12, and then into the early analog computers that would guide jet bombers through the 1950s. Few remembered that one of those devices had once been studied, wire by wire, in a darkened hangar outside Tokyo. But within Japan's technical universities, the memory persisted. Professor Takayanagi, who had written during the war that the device presupposed an electrical civilization, used that phrase again in his lectures at Tokyo University in 1948, this time as a call to action. If we are to live, he told his students, we must become that civilization. The irony was profound. The very instrument that had guided bombers to destroy Japan's cities became a model for rebuilding them not in form, but in spirit. The lessons drawn from the Sperry Autopilot flowed quietly into Japan's emerging electronics industry. The obsession with miniaturization, the discipline of feedback and control theory, the insistence that every component must serve the system all echoed the discoveries made among the wreckage of the B-29. By the mid-1950s, companies like Hitachi, Toshiba, and Matsushita were producing gyroscopes and servo mechanisms for civilian aircraft. Within another decade, Japanese firms were exporting some of the most reliable autopilot systems in the world. The engineers who had once stared in awe at the captured American device now designed their own with equal precision. They had caught up to the 10-year gap that Ueno had spoken of, not through imitation alone, but through a recreation of the industrial harmony that made such machines possible. In retrospect, historians would come to see the episode as a small but telling parable within the vast tragedy of the Pacific War. The B-29's autopilot was not a decisive weapon. It did not win battles by itself. Yet it represented something larger, the triumph of integration over inspiration, of system over heroism. Japan's wartime engineers had been taught that perfection lay in the individual craftsman's touch. The captured device revealed a different kind of perfection, one born of collective precision, where even the smallest resistor mattered as much as the pilot it served. When Lieutenant Commander Ueno died in 1962, his colleagues placed on his desk a framed note copied from his wartime journal. It read simply, "We studied the machine to understand the enemy. We discovered ourselves." Outside his office window, the runways of the rebuilt Tachikawa airfield shimmered in the summer heat. Training aircraft rose smoothly into the sky, their wings level, their course steady, held true by the quiet rhythm of the very technology once thought impossible. The last surviving page from Lieutenant Commander Ueno's wartime notebook is dated simply, Tachikawa, September 1945. The paper is yellowed now, preserved in the archives of the National Museum of Nature and Science in Tokyo. The handwriting, neat but unsteady, fills half a page. The final sentence reads, "To control the sky, one must first control the unseen." For Ueno, the unseen had not meant spirits or destiny, but feedback loops and signal currents forces, as invisible and powerful as the jet streams that had carried the B-29 across oceans. That single line captures the quiet revolution that began not with a bomb or a treaty, but with a handful of broken instruments on a workbench. When those engineers gathered around the captured Sperry device in the summer of 1944, they thought they were studying an enemy weapon. In truth, they were confronting the future. Every wire, every gyro, every relay they handled belonged to an idea of war and of progress that Japan had not yet conceived. The idea that intelligence could be mechanical, that precision could replace valor, that systems could think. The revelation did not come in a flash of victory or defeat. It arrived slowly, through the act of comprehension itself, through the realization that the instrument's perfection had been forged not by genius alone, but by a vast industrial symphony of scientists, machinists, and engineers working toward a common standard. In the ashes of 1945, that symphony became the model for Japan's rebirth. The engineers who once dissected the enemy's autopilot would later design record players, radios, and navigation systems with the same devotion they once gave to their war machines. They no longer sought dominance through destruction, but mastery through precision. By the 1960s, the rhythm of gyroscopes had been replaced by the hum of transistor circuits. By the 1980s, by the whisper of microprocessors. Yet the philosophical core remained unchanged. Faith in systems, in feedback, in the harmony of the unseen. It is difficult to separate irony from inevitability. The B-29's autopilot, built in Brooklyn to guide bombers over Japan, became through defeat a blueprint for Japan's technological ascendancy. The same principles that once leveled cities would later stabilize aircraft, cameras, and satellites bearing the label "Made in Japan." The world turned, and the lessons of war became the logic of peace. In the archives of the U.S. Air Force Museum at Wright-Patterson, the technical evaluation report on the Sperry A-5 concludes with an almost casual line: "System performance exceeds expectation." It is a dry statement, written by an engineer, but it could serve equally as an epitaph for the century that followed an age when machines began to mirror the precision of the minds that built them. And somewhere in that long chain of inheritance, between the roar of propellers and the silence of circuits, lies the memory of that hangar at Tachikawa, the smell of oil and ozone, the quiet hum of a salvaged generator, the steady gaze of men who, for the first time, saw the future not as prophecy or myth, but as circuitry. They had wanted to capture an enemy secret. Instead, they captured a reflection of what they would one day become. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.